अभी लगाने को आप देखेंगे फेसबुक पे लाइव आ गया, जरा देखें, आ गया। ये कोई है जैन अली, असिस्टेंट म्युनिसिपल ऑफिसर, आने वाला रजिस्टर्ड है, इंटर कर दो। फेसबुक पे तो आज अच्छा आ रहा है। (23) पार्टिसिपेंट्स से की रजिस्ट्रेशन कराई हुई है हमारी, और इस वक्त 10 हैं, तो 3-4 और आ जाए तो इंशाल्लाह जी हम शुरू करते हैं इसको।
जी अस्सलाम वालेकुम।
जी कमर साहब, क्या हाल है आपके?
सर अल्लाह का शुक्र है, आप कैसे हैं सर? ठीक ठाक हैं?
ठीक है, आप तो सुना है 7 समंदर पार बैठे हुए हैं।
जी सर, हमारा तो अभी फजर की नमाज पढ़ के फारिग हुआ हूँ जी।
हाँ जी, वही मैंने कहा आपका तो बहुत और टाइम है माशाल्लाह, फिर भी आए, ये जज्बा होता है।
सर वो 30th लेक्चर में भी मैं यहीं पर था।
अच्छा,
तो माशाल्लाह बहुत मजा आया था जी। आज अल्लाह ताला का शुक्र है कि अभी यहाँ पर अच्छा टाइम है। अब तो मैं इस वक्त मैरीलैंड में हूँ, तो ये 5 बजे हैं, वरना उस वक्त वहां पर इलिनॉय में तो 4 बजे हुए थे लास्ट
अच्छा,
लेक्चर में। अब तो काफी टाइम बेहतर है।
नाइस, नाइस, वेरी नाइस टू सी यू जी,
थैंक यू
माशाल्लाह।
सर, सो नाइस ऑफ यू। ये आप लोगों की हिम्मत है जी, जो आप इतना अच्छा ये अरेंजमेंट कर लेते हैं। थैंक यू सो मच सर।
पर ये अल्लाह की कुदरत है, चला रहा, वो हमें जज्बा भी दे रहा है, रिसोर्सेज भी दे रहा है, और हम किसी तरह चला रहे हैं इसको। और अभी और भी कुछ करना चाहते हैं। देखें मेरे साथी एक सुहेल की बिया यहाँ आपको नजर आ रहे होंगे, और रिजवान मिर्जा। अस्सलाम वालेकुम मियाँ साहब, हमारे टीचर भी जी मियाँ साहब, वो भी तशरीफ, इनका भी आप
मियाँ
जज्बा
साहब तो
देखें।
सर हमारे भी टीचर रहे हैं जी। आई एम फ्रॉम यूईटी 70 यूईटी था मैं तो।
हाँ जी, उनको
मियाँ
आपका
साहब हम
तो आपका नाम तक याद होगा, कमर अली जैदी।
सर, उनको मेरा रोल नंबर भी याद होगा, और ये भी पता होगा मैंने मार्क्स कितने लिए थे फाइनल में। अस्सलाम वालेकुम सर।
वालेकुम सलाम।
मियाँ साहब जी हमारी सोसाइटी के जो है चेयरमैन है, और चेयरमैन है, और इनका जज्बा है जो ये चला रहे हैं, हमें गाइड कर रहे हैं, हर जगह मौजूद होते हैं, जहाँ इनकी जरूरत होती है मौजूद होते हैं।
जी अस्सलाम वालेकुम, सुहेल किबरिया है। मैं बड़ा मजे से सुन रहा था मियाँ साहब। सर अस्सलाम वालेकुम एंड अस्सलाम वालेकुम टू ऑल टू। ये तो इस तरह कर रहे हैं हमारे मोहतरम उस्ताद मियाँ साहब कि जैसे कोई इनके पास चिप या सेंसर लगा हो कि उन्हें पता होता है कि कौन इस वक्त क्या कर रहा है।
ऐसी तो कोई बात नहीं।
सर ये मतलब ये
हाँ, इस वक्त मुझे पता है, इस वक्त आप कंप्यूटर पर बैठे हुए हैं कि इस वक्त क्या कर रहा है। इस वक्त आपके मुताबिक मैं झूठ कह सकता हूँ। आप
सर मैंने एक्स्ट्रापोलेट किया सर, वो होता है ना एक्स्ट्रा सेंसरी परसेप्शन में, मेरा इशारा उस तरफ था।
फेसबुक पे आ रहा है ना। चले अब हमारे पार्टिसिपेंट अब हो गए हैं हमारे पास 14 मिनट बचते हैं, 2:03 है। तो आप फेसबुक पे ठीक है ना, आवाज भी ठीक है, कोई टेक्निकल हिच तो नहीं कहीं पे? चले ठीक है। Bismillahirrahmanirrahim. Gentlemen, I welcome all of you in the lecture number 31 of Pakistan Society of Civil Engineers. Today, our guest speaker is Dr. Muhammad Irfan, and today's topic is prediction of early warning of landslides. Prediction and early warning of landslide. Before I introduce the speaker to you, as usual, there are certain rules we have to follow during the lecture. Just a minute. Sorry, I'm
Tahir sahab, your sound was all right a little earlier, but now you see there has been a lot of.
I would request you to unmute their microphone. Please mute. सादी आपका तो नहीं।
साहिब साहब, मेरा ख्याल है आपके पास है दूसरा सिस्टम भी पड़ा है और वो अनम्यूट है, तो वहां से एको ज्यादा हो रही है शायद।
नहीं सर, मेरे पास सर मेरा म्यूट
नहीं, म्यूट नहीं है आपका, वही प्रॉब्लम क्रिएट कर रहा है। अब ठीक है, अब ठीक है। दिस इज ओके। Sorry, ji, the problem was at my end. My colleague, Miss Sadia, her mic was not in a mute position. Now it's okay. Okay. We started this right again. It is lecture number 31. I welcome all of you. We now have a lady and all gentlemen. A very warm welcome to all of you from Pakistan Society of Civil Engineers. Today's lecture is being given by Dr. Muhammad Irfan, and this is lecture, as I've said, it is lecture number 31, prediction and early warning of landslides. As I was going to start to tell you the rules of this session, so we got a technical hitch. Now I think everything is okay. So the rules are that all the aspirants of CPD certificate have to appear online live on their webcams. This is a rule which has been set by Pakistan Engineering Council, and they are very strict on it. So please, everybody should appear live on their webcam. I and my colleague Sadia should be able to see you online. Second is, during the lecture, the microphones of all the participants shall remain in mute position so that we do not hear any background sound, and the speaker can deliberate in a smooth flow. Third, the question answer session, we have a slide change here. The speaker will prefer that you should ask the questions during the lecture, but not during the lecture, but at a certain time. He has divided his lecture into 2 or 3 parts. So at the end of every part, speaker will allow you to ask questions. He will give you about 5 to 6 minutes to ask the questions. You can ask them. Well, you can. I will moderate those questions, and better you write it in the chat box as we do it in a routine, and I will read those questions to the speaker and then he will answer. Now, once his lecture is finished, then at the end we will have our normal question answer session of 20 minutes. There again, you can ask your questions in detail, and you can ask your questions in your voice through the microphone. But during the lecture, when you are given the time for asking questions, I would request you that you should type the questions in the chat box and I will read it for better control and moderation. Again, I will request all the microphones to be in a mute position so that there is no background noise and speaker can deliberate smoothly. Now I will introduce the speaker to you, and then I will hand over the floor to him. As I have said, today's speaker is Dr. Muhammad Irfan. His educational background, first I will tell you, he did his undergrads in 2008, BSc Civil Engineering from UET Lahore. Then in 2011, he completed his master's in the same university, UET Lahore. In 2011, he proceeded to Japan and got his admission in the PhD program in University of Tokyo, and he went there on a mixed scholarship. Dr. Saab completed his PhD in 2014, and his thesis was elastic wave propagation through unsaturated soils concerning early warning of rain-induced landslides. Dr. Saab is still, I think, affiliated with the University of Tokyo as a postdoctoral research fellow. His professional experience is from 2008 to 2011. He was a lecturer in Civil Engineering Department of UET Lahore. And after that, as he proceeded to Japan for his PhD program, he was an active member of English Writing Consultant Group in University of Tokyo. He was a teaching assistant in School of Engineering there. After returning to Pakistan in 2014, he served as assistant professor in Civil Engineering Department of UET Lahore from 2014 to 2018. And there he also was providing some professional consultancy on various projects. There are a number of projects, but I will name you a few. He was involved in Ravi Riverfront project. There, I think he did the stability calculations for the embankment seepage studies, design of foundations, and review of geotechnical investigation reports there. He did the detailed engineering design of Gorano Dam, which is in Thar, province of Sindh. Then 180 megawatt combined cycle power plant in Bhiki. That's a very famous project. He was also involved in the geotechnical investigations of Angro gas compression project in Guddu, feasibility study of 98 megawatt Batakundi hydropower project, 147 megawatt project in Petrin, Azad, Jammu Kashmir. I was also involved in that project, 147 megawatt hydropower project, and he designed the surge shaft access road there. And then he did some, he was involved in geotechnical investigations of various grid stations of NTDC up to the voltage of 500 kV. And in Lahore, he was in, it gave his geotechnical expertise on Orange Line metro train projects and pile load testing for Orange Line metro projects. And there are a few other projects also similar to what I have already described. Now, currently, he is the Chief Executive Officer of Birudo Engineers, where he is handling the same type of projects, landslide study in Gilgit-Baltistan province. Then he is involved with the geotechnical studies of hospitals, schools, industrial buildings, hydropower projects, and like this, many other projects too. He is a reviewer of International Springer International Geomet, International Society, Iranian Society of Civil Engineers. Reviews of four publishers, that is Elsevier International, Springer International, Geomet International Society, and Iranian Society of Civil Engineers. He is an author and co-author of 23 publications, and he has attended, mashallah, 21 conferences in Korea and France, where he has read the history. So this was a brief introduction of Dr. Saab. Time constraint, go quickly over his introduction. There's much more to tell you. I think some other time, inshallah, we will have more time. I would again request, there are certain mics which are still in a They are not in a mute position. Please. Before I give the floor to Dr. Saab, please put your microphones in a mute position. I humbly request everybody to listen to me and please put your mics in a mute position. And there are few participants still who have not switched on their webcams. Please follow the instructions. We will wait only 5 to 10 minutes after the lecture has started. The people must appear on the webcam live, who are the aspirants of CPD certificates. Thank you very much. Dr. Saab, the floor is yours.
Thank you very much, Taisa, for the kind introduction. I'll share my screen in a minute. Okay, so is the screen visible, Taisa? Is everything clear? And am I audible as well?
Yes, your screen is visible and you are audible.
The screen is
Okay,
visible. Please continue.
Okay, thank you very much. Thank you very much, Taisa and Pakistan Society of Civil Engineers, for providing me with this opportunity to introduce this innovative yet modern topic, which is gaining a lot of popularity worldwide. Many different countries, they're working on this thing. And I think it's time, high time in Pakistan as well, for us to know more about this area and in fact, try to implement this as well. So early warning and prediction of landslides. What I've done is I've tried to break down my presentation into a number of sections, which you can see here. And I will try that at the end of section B and at the end of section C, we will have a brief question answer session. And then in the end of the whole presentation and whole discussion, we'll have a detailed question answer session as Taisa explained. So to begin with, as we all know that landslides are a common natural hazard that we have to face across the world. There are some numbers which show that the overall damage which is caused by landslides exceeds several billions of dollars. But sir, I think some mics are not mute, so if you can get them muted, please. Okay, so these facts which I've written here are something which many of us already know, but something that most of us don't know is that large number of these landslides are actually triggered by rainfall. Yes, there are other triggering factors like earthquakes and human activities, etc., but a majority of landslides around the world are triggered by rainfall. And then there are certain specialized characteristics of rain-induced landslides. And these characteristics basically are that the rain-induced landslides, they are small in size, but in any particular area, there are a large number of small size rain-induced landslides which are there. And these characteristics make it very unique, and it makes it very different compared to the earthquake-induced landslides, for instance, which are generally large in scale. Why it is important to tell you this thing in the beginning is because you will see that a lot of prediction methods that I will be discussing are mostly focused on rain-induced landslides specifically. This has been the global trend which has been practiced. Landslides are not uncommon in Pakistan as well. We have all seen these examples in the news headlines over the years. I've just shared a few examples here in these figures, in these images, but we all are aware of the damages that landslides cause almost every year in Pakistan. And while talking about landslides in Pakistan, it will not be complete without the discussion of the Atabad landslides, which Okay, so Atabad landslide, which was triggered in 2010, and it caused a huge catastrophe in the whole, in greater part of Gilgit-Baltistan region. And in fact, we know that a landslide dam, which was made, which is somewhere here, its height was around 109 meters. And because of this landslide, in fact, some of our existing dams, some major hydropower projects like Mangla and Tarbela, they were once thought to be affected because of this. So this is just to emphasize the importance of landslides and our ability to predict these landslides. Now, so moving on to prediction of landslides, what basically landslides are, what are the different benefits and methods. You can see this animation from USGS, which shows a landslide which somewhere in US. And what you can observe from here is that a landslide, which we generally know as happened all of a sudden, it does not happen all of a sudden. In fact, what happens is there are small changes which are occurring in the soil, which are not visible to the naked eye. And since they are not visible to the naked eye, so we are unable to observe them in a timely manner. And we only know of a landslide when the landslide has actually occurred and the damage has already been done. So this is why if we have some sensors or instrumentation or prediction methods, which can tell us something in advance, it can be of a lot of benefit for us. So what are the actual benefits that we can get from the landslides? So basically there are three kinds of benefits which we can get from early warning of landslides. And the first one is that if we know or if we can predict a landslide, we can devise some methods for their mitigation. If we know when the landslide is going to happen, and if we know if the slope has started to move, we can devise some methods and we can try to mitigate it. But this is not always possible. A number of times, the early warning or the early warning gives you only a small time. And if it gives you small time, you obviously cannot do the mitigation methods. Then at least we can evacuate people from there. So we can save human lives, and we can probably save some construction equipment, etc., from there as well. And the third thing is that if we are able to detect the movement of the slopes by using this information, we can also make informed decisions regarding the construction of future projects. So if you want to construct a house somewhere, but you are worried that the slope, which is uphill side of that house, of the property that you plan to purchase, is possibly moving. If you are able to get some data of the sensors of that slope, it can give you a good decision-making thing that whether this slope is moving or not, is there any danger of a landslide? So can you buy that house or not? This house is a very small example, but obviously this can be a very important thing in case of mega projects. So this kind of information can be very helpful for us. Now, if we know the benefits of landslide prediction, then what are the different prediction methods that we have? Basically, there are three basic methods for landslide prediction. The first one, and I'm describing these in order, in a chronological order, in an order in which they have evolved historically. The first one is by using the rainfall thresholds. Second, by using the landslide susceptibility or landslide hazard maps. And third one, which is the modern one, which is real-time monitoring through instrumentation. So what I will be doing in the following slides, I will be trying to explain these three one by one. So what do we mean by rainfall thresholds for landslides? Now, the need for landslide prediction was originated long time ago in 1970s. People started observing this, that a number of landslides occur after every rainfall event. But so they thought that it would be worthwhile to try and predict when a landslide is going to happen, so that at least they can reduce or minimize the damage that is caused by the landslides. So for doing this, they did not have any instrumentation back then. So what they did, they could only gather the rain data over there. So by using the rainfall data, they tried to predict the landslides. And some of the earliest examples, for example, is shown in this graph, which was used by Japan Railways back in the day. So what they had was this kind of a simple graph in which the x-axis had the total rainfall in any event, and the y-axis showed the intensity of rainfall. And simply by looking at any particular rainfall event, which zone you are lying, you can decide whether you can continue with the train operations, or you have to operate with caution, or if you are in this zone somewhere, you have to stop the operations because it can lead to landslides. So this was one of the earliest examples. This is from Japan, but we have similar examples from other parts of the world. For example, this one in Hong Kong, they also use a similar kind of thing. They saw that it's not only a single rainfall event, rather most of the times rainfalls come in events which are spread over several days. And if this is the case, so they used 15-day rainfall on the x-axis, and on y-axis, instead of the rainfall intensity, they used the 24-hour rainfall. And they developed a similar kind of a graph in which you can have a current rainfall event, and you can plot your point depending upon the 15-day rainfall and the 24-hour rainfall, and you can see whether you should expect some minor damage, some severe damage, or you should expect some disaster from it. So this was historically what people used to do. And this actually graph, which looks quite complicated, what this graph does is actually it summarizes the global thresholds for based upon the rain-induced thresholds. This graph actually summarizes all the historical thresholds.
Dr. Saab, I am really sorry for the interruption. Please bear with me a minute. Hey, Mr. Furqan and Mr. Sajjad Saeed, you have been reminded so many times to switch on your camera. I don't know how, now in what language I should tell you. You know, we cannot afford to have somebody who has to be issued a CPD certificate and he does not appear live on the cam. So please understand our situation. Pakistan Engineering Council is very strict on it. This is the facility of conducting online seminar has been given on the condition that people will appear on the webcam live. So we cannot afford to see you, to admit you in this room without seeing you. Please, either you come live on the cam or you will not be issued the certificate. You can continue to sit in this room, but the certificate will not be issued to you. Thank you very much. Dr. Saab, continue, please.
Thank you. So discussing about this graph, we were seeing that all these lines are actually representing the thresholds for rainfall, for possible failures from around the world. What it means is, if you are below this line, you are not expecting to have any failure or a landslide. And if you are above this line, you should expect to have a landslide failure. Now, the problem with this is this graph gives us very unique information. And what information it gives is that we can see that that historically in different countries, people were doing this effort to predict the landslides, but all of us were getting very, very different results. You can see all these lines are not matching with each other. Now, what could be the possible reason? The possible reason basically is that how these graphs are made is simply based upon the historical record of rainfalls. So historically speaking, they saw that when the 15-day rainfall was around 500 millimeters, and for 500 millimeters 15-day rainfall, whenever the 24-hour rainfall exceeded 100 mm, there was a disaster. So possibly they observed this somewhere in Hong Kong, but maybe in another country, the response was different. And not only in different countries, in fact, even in the same country, in different regions for different slopes, the response was very different. And the main reason was the landslide does not only depend upon the rainfall intensity and the duration of rainfall, but it also depends upon a lot of other factors, which are like the soil, the characteristics of the soil stratigraphy over there, the slope angle, its directions, and the land covers, etc. So all these factors were not considered, historically speaking. So this is a huge drawback which the world was facing. And then, in fact, there was another big issue. The other big issue was that, okay, we have said that if there was 500 millimeters of 15-day rainfall, and let's say there was 200 millimeters of 24-hour rainfall, so someone has said that there was a landslide. But the problem is that the rain gauges which are used to identify these rainfalls are most often are located much farther away from the slope itself. And in that case, the actual rainfall at the landslide location can be very different. Another thing is that since the landslides occur at very remote places mostly, so we did not have very clear account of when the landslide actually occurred. Point being that people used to say, yes, in the last rainfall event, maybe 4 or 5 days ago, maybe 4 or 5 days ago, there was a landslide somewhere. But they cannot pinpoint the actual time when the landslide occurred. So these were some serious challenges for actual prediction of landslide. You see, what I'm trying to do is, in today's day and age, we can actually pinpoint and actually tell the landslide. In fact, I'll share a couple of case histories where merely having an early warning of 2 hours was enough. But what was happening in the past was people were just telling that maybe 4 or 5 days ago that landslide occurred. So because of these things, there was a lot of unreliability which was associated with the landslide prediction. So this was the first way of predicting landslides using the rainfall thresholds. Afterwards, what people did, they said that a better way would be to develop landslide hazard maps for the whole areas. So what they did, for example, this is a landslide hazard map for Italy. And if you see what they did, they tried to improve the deficiencies of the previous method somehow into it. And this was actually made possible with the advent of advanced computing powers. So what they did, they had a soil map available with them. They had an elevation model available with them, which we know a DEM can be easily available these days. They had a geological map available with them. They also had a historical landslide map available with them. Now, by running a multivariate analysis, by assigning weights to the importance of these parameters compared to the landslide, by doing some of these rigorous analysis, they ended up with this kind of a graph. Now, this kind of a graph, what it tells is, it simply tells that what is the probability of landslide somewhere. So as you can see below, simply red gradient shows a high probability of landslide and vice versa. So we ended up with these kind of graphs in the long run. And I'll just show you in the next slide a few more examples of this kind of graphs. So this was Italy. Similarly, this is a graph for Nyland in Philippines, where they assigned similar probability of possibility of landslides. And this is probably a better one, which is for the entire United Kingdom. And in fact, this has been issued by the British Geological Survey. And you see, since this is rather more detailed, where they mention, where they give more detail after performing much more rigorous analysis there. So this is what has been stage 2 of landslide prediction, what has been done. Another important point that I feel over here is that these kind of maps, as this map that we are seeing here, which has been established by British Geological Survey, the developing countries like Pakistan, we lack any such kind of information. So since at the government level or at the institution level, there are no such maps available, but a lot of researchers have developed such maps. For example, this is one for a place near Sakardu, Shigar. This is a landslide susceptibility map for Shigar. And this one is very interesting, in fact. Why so? I say so because this is for the entire Muzaffarabad, Azad Jammu Kashmir. And this is actually, I've taken it from a paper which is published by PSCE journal. And as people who are linked with economics, they know the PSCE has a very rigorous technical review process. So it means that people who have published this would have undergone a significant, quite a stringent review process. So if at the government level, I sometimes think if at the government level we cannot do this kind of research, it cannot involve universities to do this kind of research. So probably what can be done is that this kind of maps, which are already available for some areas, all we can do is we can at least disseminate them for the general public for their benefit. So these are some examples from Pakistan, and then finally, this is an example from the world's largest landslide hazard map, which has been developed by USGS, in fact, which has been developed by NASA by using the data from USGS. So what USGS did, they have an online portal which you can access on their website. And from there, you can get data of all the landslides in the last 12-15 years. So they have around 12-15,000 landslides over there. By using that data, which we can see plotted here, by using this data, and then also seeing the fatalities that have occurred over there, the size of these the size of these circles actually show the number of fatalities caused by each landslide. So by using these graphs, they were able to predict, they were able to come up with this kind of a map, which we can use for landslide susceptibility. But still the problem remains. The problem remains, yes, we have got a landslide hazard map. It gives us a good overall impression of any particular area. But the problem is that it cannot tell me local changes. And can I use it for early warning as well? Yes. Or can I use it for early warning or prediction? The answer is no. Obviously, I cannot use it for early warning and prediction. So what is stage 3 for landslide early warning? That is basically instrumentation-based monitoring. Now, what is instrumentation-based monitoring? In order to explain the overall concept, let's consider this example that is shown here. So let's suppose there is a slope which has some houses at its toe and some other structures somewhere. So what we do is we install some sensors over there, a sensor which is shown here. Here, these other sensors, I'll explain them more in detail. We have a rain gauge installed over there as well. So what happens is when rainfall occurs, the rain gauge starts recording the amount of rainfall. And once it does not only record the amount of rainfall, but what it does is that it also, these sensors, they are also observing the changes in the slope itself. So these sensors, what they are doing is they are observing the changes in the slope. And when these changes in the slope reach a certain critical value, they issue a warning. They transmit the data to the mains, to the server there, and which can transmit the data to the headquarter, which can be a municipality office somewhere, and you can issue a warning to the people living in that area. So this is the basic concept of instrumentation-based monitoring and early warning system. This is the overall concept of it. Now, the question comes, okay, we can install these sensors, we can issue a warning this way, but the question comes that what are the things that we need to monitor? If we want to have an efficient early warning system, what are the things that we need to monitor and see in the slope itself? So researchers have came to a conclusion that basically these are the two things that we need to look when we want to predict a landslide. The two things are the actual displacements or the movements in the slopes, and the second is changes in the soil moisture. So these are the two things that we need to see if we want to predict a landslide. Now, okay, we want to see the displacements and we want to see the soil moisture, changes in the soil moisture. The next question is how to do that? What kind of sensors do we use to measure the displacements, and what kind of sensors do we use to measure the soil moisture? So what I'm going to do here is there are a lot of different kind of sensors which are used for each of these purposes, but I'm going to generalize things here a lot and going to simplify it and share with you the most popular ones only. So for displacements, there are two kinds of sensors which are commonly used. One are called the inclinometers, the other are called the extensometers. If I'll share more detail of these later on, but this is how an extensometer looks like. It is installed on the slope surface. So it is installed on the surface. And by installing on the surface, it tells how much the slope is moving, how much the movement is there. And whereas the inclinometers, they are drilled into the ground, kind of drilled into the ground. And when the slope moves, they see the movement and they record the movement. And this is how they observe the displacement in the slope. Talking about soil moisture, basically there are two different kinds of sensors. One is called the dielectric moisture sensor, which is very common. The other is called the tensiometer or the suction cups, which are used. So in the next slides, I'll try and share some details of these. So let's first look how can we measure the displacements by using inclinometers and extensometers. Let's try to see some more details about these. So the displacement sensors, the inclinometers, this is how an inclinometer typically looks like. It is simply a rod which has some assembly here, which is actually to keep it in its place when it is inserted inside a borehole. How do we install it? We first drill a borehole. We insert a certain casing, which is a specialized casing for this kind of inclinometer, and then we simply push it inwards. This is how we do it. And how it works, for example, if here we have an inclinometer installed, when the slope starts moving, when it starts sliding this way, it pushes the inclinometer with it. And when it pushes the inclinometer with it, these deformations, these changes are observed by the sensors and are communicated to the servers. So this is how the inclinometers basically work. So this is the first kind of sensors that we use. The second kind of sensors are known as extensometers. So the second kind of sensors that we use are extensometers, and this is how the extensometers look like. As I told earlier, the extensometers are installed on the slope surface, and there are two basic parts to it. One is installed on the stable part of the slope, and other is installed on the moving part of the slope. So this part is on the stable part of the slope, the other part is on the moving part of the slope. So once the slope starts moving, this moving part pulls this string which is attached with the fixed part, and this extension of the string is actually what is recorded by the sensor. And the basic problem with these kind of extensometers, as you can see in this picture, one, their installation is quite difficult. The second thing is that these extensometers, it is very difficult to maintain them because you might have to install them at a remote place, as you can see in this picture. So the problem is that maybe animals or other, even by human activities, it causes a huge obstruction there. So since we have to leave them at that place for maybe for several years, as long as we want to monitor the slope, so it becomes quite a challenging task to maintain these extensor meters. However, from research viewpoint, it has shown that these extensor meters are very reliable and provide us very good information about the slope monitoring. So once we have known what are the displacements, the second thing is how to determine the soil moisture. So for measuring soil moisture, we have the two kind of sensors. One is known as the dielectric moisture sensors that we have over here. And this is how the dielectric moisture sensors look like. So what they do is, you can see there are two probes at the front. It has either 2 or 3 probes as seen in this image. So when it is inserted into the ground, the change in electric conductivity of the soil, which is between these 2 or 3 electrodes, is what makes us see how much moisture content is there. So it simply passes electric current from one probe to the other probe. And if the moisture changes, the electrical conductivity of the soil, which is between these probes, it changes. So this is how it measures the moisture content within the soil. The second one is a little more complicated, which is called the tensiometers or the suction cups. They measure the metric suction of the soil. This is how they look like. This is how we insert it. No, I cannot explain it a lot right now because we probably don't have much clarification on the concept of metric suction. And this metric suction is something which I will try and explain in the next section of this presentation. So this is about the kind of sensors that we use for instrumentation. And the next thing is that what is metric suction, and in fact, why metric suction is important, why it is important to measure metric suction, even why it is important to measure soil moisture. What role does it play in landslide monitoring? Until unless we understand the role these things play in landslide occurrence, we cannot have a good idea about why to monitor them and where to monitor them. So in order to give a brief introduction of this, in the next section of this presentation, I'll try to explain some basics about the unsaturated soil mechanics. So if we have some basics of unsaturated soil mechanics, we will then be able to understand how a landslide actually occurs. What is the mechanism that is going on within the slope for the landslide to occur. So that's the end of my part 1, and we can have a brief question answer session. I would request Tahir Saab to moderate it. I would want it to be finished in like 5 to 7 minutes probably, so that I can complete the rest of the content within time as well. Thank you very much.
Dr. Saab, we have questions for this session, and I have 3 questions at the moment, and they have been asked by Muhammad Imran. First one is, what tools are used to predict landslides? I think you have already shown them. So if you want to still say something, please go ahead.
I think I've already showed the tools that are used. So probably that already answers the question.
And the second question is, which I could not fully understand, but maybe since it's your subject, you might be able to understand. What was the fastest landslide?
What was the fastest landslide? I think that's, I do not have any numbers on it, to be honest. But I think at the end of the next upcoming section, when I'll explain the mechanism of rain-induced landslide, probably the person who has asked this question would get his answer, because there are certain things that have to change within the soil mass itself, and it only depends how quickly these things can change. And I'm restricting my answer to rain-induced landslides only. In case of earthquakes, probably we have very fast landslides, because as soon as there is shaking, there's a slope failure. So I think if you ask in isolation, the earthquake-induced landslides are typically the fastest. But if you want to know more about the rain-induced landslide, that probably will be covered in the next upcoming section.
Okay, the third question is again by Mr. Muhammad Imran, and he is asking, what are the human activities that trigger landslides?
Again, it's although it's a very simple question, but at the same time there can be a lot of answers to it. So if you want a generic answer, so a generic answer can be if we start removing soil from the toe of the slope, that obviously is going to trigger a landslide. Or if we start if we start increasing the moisture content in the soil in a localized place, that is something that can trigger a landslide. So this is again a generic kind of a response. But again, once we discuss more about the mechanism of landslide, maybe you can get a better picture of this thing.
Yeah, again, now we have the question from Mr. Imran, and he's asking why rainfall is the most common trigger of landslides around the world. Well, it has to be. Anyhow, please answer.
There are certain things for which we don't know why, but we have the numbers to prove that. So to answer this question, this is based upon statistics and numbers. So I don't know why other factors do not cause so many landslides. Maybe because there are more rainfalls and earthquakes in the world. That's why. So this is what I can say.
Yeah, and we have a question from Hassan Khan. He is asking what probabilistic methods are used to predict them, most commonly used. Predict them means to predict landslides.
Yeah, actually, there are no such probabilistic methods you can say, because there are no hardcore probabilistic methods, as that is what I'm aware of. What generally people do is, let me go back to a slide that I want to show here. Just a second. So what mostly people do is they involve the probability of occurrence of a particular landslide in these kind of maps. So once they are doing this multivariate analysis, so among a number of variables that they are considering, they are also considering probability of occurrence of a particular landslide. So this is probably what they are doing, and they're already embedded in these kind of probability maps. So there are no separate probabilistic methods that at least I'm aware of.
Dr. Saab, we have Dr. Suhail Yusuf among the participants, and he is asking question: did you test these sensors in the real world? What was the accuracy?
Yeah, that's a very interesting question, and in fact, this is what I'll be showing a couple of case histories where we actually installed these sensors. We have installed them at so many sites, maybe more than 25 to 30 sites at least, or maybe even more than that. In fact, a couple of years ago, we installed them once in Pakistan as well. So I'll share all these details in the end of the presentation.
Okay. Now we have a question from Mr. Ahmed Qadri. Again, he's a very senior fellow here among the participants. But his question is slightly off the subject, but needs, I think, expanded answer. I don't know whether, but I will read the question, please. How can we generally control the construction malpractices in the north, which often result in the initiation of landslides?
I think
if you can answer it briefly, please. I think he has a point there, but let's answer the question.
I totally agree that he has a very valid point. But I think to answer this question in the shortest of the words, what I could say is we need to understand and educate common people that what are the things that cause landslides. And if general people understand that this is the triggering factor of a landslide, then it would be easy for them to implement, not to do those things. So I think this is the simplest answer to this.
Now we have a question from Suhail Kibriya, who's a very senior geotechnical engineer in our country, and he's in the participants. He is asking, have magnetic probe extensometer also been used for such prediction systems?
Actually, I think people would have used it somewhere, but I don't have experience for that, so I cannot say anything. I think I probably came across some research from people in somewhere in Switzerland who might have used it. I don't have much information about it.
Next question is from Mr. Zahir. He is asking, does rainfall gauges data still play a vital role in landslide prediction?
Yeah, before answering this question, Taisab, I think this would be the last question for this, and then we can continue with the rest, right? So yes, rainfall data still is important, and again, I'll show some case histories, and from there you can understand that rainfall data is important, because what we try to do is we try to correlate the rainfall data with the changes in the soil moisture. We try to predict, okay, if this much is the rainfall, so this would be the change in soil moisture there. And then we try to connect the changes in the soil moisture with the actual physical deformations which are occurring on the slope. So I think this is why it is important.
Okay, Dr. Saab, you can now continue with your lecture. I have still 4 questions, but that we will take it to the end. Thank you. Continue.
Thank you. Okay, so let's see how the landslides actually occur. What is the mechanism of landslides?
I have to make one announcement, please. Just a second. We have viewers on, as you know, this transmission is going live on Facebook also. So there we also have the viewers. So all participants on Facebook are informed that they can ask their questions on Facebook also. It is being monitored by one of my colleagues, and whatever questions you will ask, I will read them here. We will note them down and then read it here, and you will get the answers to your questions at the end of the session. Thank you.
Okay, so in order to try and understand what is the mechanism of landslide, rain-induced landslide that is, and how it occurs, we have to get some basic information about the unsaturated soil mechanics, because this is something that we generally are not much aware of. So I've tried to give you a very quick basic introduction of unsaturated soil mechanics here. If you look historically, the human civilization that has evolved historically, that has always evolved somewhere close to the water. If, for example, this is a very interesting image of Cairo city, and you can see all the development along River Nile. So the presence of water has been a very important factor. And similarly, if we look at some of the large metropolitans around the world, you would see that there are always rivers and major water channels which are flowing probably somewhere from the middle of the city there. And this is not something that we see abroad. Even if we look in Lahore, we have River Ravi flowing right next to it. Now, what happened was that if we are close to the water channel, water tables are generally shallow and soils are more close to saturation. And as we start moving away from water, as the cities expand, you have to move away from water. The water tables generally get very deep, and the soils which were previously saturated close to the channel, now they're not fully saturated. Rather, they would be in a state which we call as the unsaturated state. So this is something which was recognized by geotechnical engineers worldwide, and they divided the soil mechanics into 2 broad categories, which they call the saturated soil mechanics and unsaturated soil mechanics. Now, we all know that saturated soil mechanics, which was much explained by Carl Terzaghi and others later on, all the fundamentals are nearly well established. We have a very good understanding of this. All the course content that we study in our undergrads is related to saturated soil mechanics. But in the last 30 years or so, this unsaturated soil mechanics, the advanced world, they are seeing more and more the importance of unsaturated soil mechanics. And they're trying to involve this in their understanding. They're doing research on it. They're trying to even include some things into their codes and evaluation methods. So I think it's a little important to give a brief introduction of this unsaturated soil mechanics there. So what is unsaturated soil mechanics? So in order to understand unsaturated soil mechanics, let's consider this very simple figure here. We have a soil strata here. This is below the groundwater table. And when we are below the groundwater table, this is the zone which we call as the saturated zone or the phatic zone. And whatever is below the groundwater table, this is what we call as the saturated zone or the phatic zone. What happens above the groundwater table? So if we want to simply define unsaturated soil mechanics, unsaturated soils are simply the soils which are above water table. So whatever is above water table, it is going to be called as unsaturated soil, and this zone is typically known as the Wadose zone. So we have the phatic zone and the Wadose zone above water. Now, what happens to the pore water pressures when we are beneath the groundwater table? When we are beneath the groundwater table, the pore water pressures are positive. And this is something what we study in our undergrad courses. There is a positive pore water pressure which is there below the groundwater table. But what happens above the water table? When we go above the water table, this whole zone is again divided into two zones. There is this smaller zone over here, which is known as the capillary fringe zone. Now, what happens in this zone is that the soil above, which is in the unsaturated zone, it tries to suck the water from the groundwater table and it tries to pull it upwards. How it pulls it upwards? It is simply because of the capillary action, something that we know because by looking at this image, you can imagine simply. So it tries to pull the water above because of the capillary action, and this is something which we call as the capillary fringe zone. And in this capillary fringe zone, the main differentiator is that this capillary fringe zone is nearly saturated. So it has at least 90% saturation, and it is very close to saturation. And however, this is much higher compared to the groundwater table. So if we look at the pore water pressure regime in this zone, we'll see that this part is still saturated. However, the pore water pressure, because it is because of suction, now it is sucking the water upwards, like we suck the water in a pipe here. So there is going to be negative pore water pressure here, something which is very similar. If I ask anyone what is the pore water pressure here or what is the pressure here, it will be the negative pressure. It is the vacuum here which is keeping the water inside this tube. So in the same way, this part is fully saturated, but the pore water pressure is negative. Now, what happens when we go above this? Above this, there is still negative pore water pressure. And this negative pore water pressure, what it does is, contrary to the positive pore water pressure, we all know that the positive pore water pressure, it decreases the soil strength. Because when the pore water pressure increases, because of the increase in the pore water pressure, the effective stresses in the soil decrease. And because of the decrease in the effective stress, the soil becomes weak. But contrary and opposite to this, what happens in unsaturated soils, that this negative pore water pressure actually tries to bind the particles close to each other. And because of this additional binding, it actually increases the strength. So I've been using this term effective stress. So I'll just very quickly try to explain effective stress to those who are not very familiar with this discipline. So In case of a saturated soil, we know saturated soils are the ones in which all the voids are filled with water. So there is soil solids represented by yellow here, and there are pore voids which are represented with a greenish or with a greenish color here. So when we apply the stress on top of it, the pore water pressure increases, and because of the increase in pore water pressure, the effective stress, which is the particle to particle contact force. This is what an effective stress is. I am trying to apply load on the soil. The soil particles are being pushed together. They are being pushed together. This is what is actually going to take the load of the building, which is going to be constructed on top of it. But this increase in pore water pressure here is actually pushing the particles away from each other. And if it is pushing the particles away from each other, it means this is how it is decreasing the effective stress. So this is what happens in case of a saturated soil. And by using this very simple equation, we can determine the effective stress. And why I'm focusing more on the effective stress, because we know in soil mechanics, it's never about the total stress that we care of. If we want to determine the deformation behavior of the soil, it's always about the effective stresses that we need to, that we are actually concerned with. So this is how the effective stresses work, the concept of effective stresses work in case of saturated soils. Now let's see what happens in case of an unsaturated soil. In case of an unsaturated soil, the mechanism changes, and how it changes. Previously, for the saturated soils, all the voids were filled with water. But now what is there? There are soil solids. Some of the voids are filled with water. In fact, you can see some water sticking to the soil particles, and then there are air voids in it as well. So there are voids which are filled with air. So when we have this kind of a scenario, how do we determine the effective stress? How do we determine what is the particle to particle contact force? Now, before I show you the equation and take you into complex stuff, let's try to understand it a little bit in physical world. In case of saturated soils, what was happening was, when we apply load on top of the soil, when we were applying load here, the pore water pressure, because it could not find any way to escape through the soil skeleton, it was pushing the particles away from each other. Now, if I'm applying a load on top of this soil, what is happening? There is pore air in it. We know this air is compressible, but still this air will be trying to push the particles away from each other. But what role does this water playing? This water, which we sometimes call as the adsorbed water as well, what this water is doing is that it is actually gluing the particles together with each other. It is actually sticking the particles with it. So because of this sticking action, the effective stress should be increased, contrary to what was happening in case of a saturated soil. So if we want to determine the effective stress in case of unsaturated soils, we now have one additional parameter. Besides the total stress and the pore water pressure, we have pore air pressure as well. And if I want to write down the equation for this, the equation for this can be written something like this: the total stress minus the pore air pressure, which is pushing the particles away from each other. But there is another thing which is involved here, and this is something which is written in this way. And what this thing is, it is basically what we call as suction, or the metric suction of soil. Now, this function is called as metric suction, but you can see what we can do is, if we are talking about normal circumstances close to the ground, and close to the ground, we can take pore air pressure same as the atmospheric pressure, or I can take it equal to 0. And if I do that, this equation becomes the same as what I was using for saturated soil. So this is something which this is how the effective stress equation for unsaturated soil mechanics work in very, very simple words. Obviously, there are a lot of other variables in it as well, but I've tried to simplify it as much as I can over here. Now, the important thing that we need to understand from here is that the behavior of unsaturated soils, it is significantly governed by this metric suction, the metric suction which is here. And how you can remember this metric suction? By remembering, in order to try to physically understand this metric suction, there's a very simple way of understanding this metric suction is by taking it as this gluing action between the soil particles. So this section is actually trying to stick the particles with each other. Thereby, it is increasing its strength. Now, the next thing is, which is actually forms the backbone of unsaturated soil mechanics. And this graph is something which actually forms the backbone of unsaturated soil mechanics. And this graph, which is known as the soil water characteristic curve. Now, what this graph is, it is simply a graph between moisture content on the y-axis and metric suction, that sticking force, on the x-axis. Now, you can see what is happening here. In this zone, for example, the soil is fully saturated or nearly saturated. All the voids are filled with water. And if all the voids are filled with water, the metric suction is very low here. After some time, if there is some air void which is introduced into the soil, because of the introduction of the air void, now the water is removed from here. So the saturated water content would decrease. So it would decrease, this graph will start coming down. But as it is coming down, because of the introduction of air here, so the water content is coming down, but with a decrease in water content, the metric suction, that sticky force that I'm saying in very simple words, the sticky force keeps on increasing. So this is the second phase, which we call as the transition zone. And then finally, a stage comes when even this little water which was there, it is almost absent from here, or very, very little adsorbed water layer is there. So in that case, we have very less water to be taken out of the soil skeleton. But despite of that, metric suction, the attractive force, it increases very significantly. So this soil water characteristic curve is something which forms the backbone of soil mechanics. If anyone can understand the soil water characteristic curve, they can understand pretty much any concept of unsaturated soil mechanics, because this is the fundamental and the basics of unsaturated soils. So what do we get from here in very simple words? In very simple words, what we get from here is, as the soil becomes dry and dry, the metric suction or the strength of the soil increases. And as the soil becomes wetter and wetter, as it keeps getting more and more moist, the metric suction or that binding force decreases. And that is something which is very common, which is very common for you as well. You can very easily comprehend that. You go to a beach, you build a sand castle, and that sand castle is made from sand which is little moist. And why does that sand sticks with each other? Why are you able to make a castle out of it? You're able to make a castle out of it because of this metric suction there, and you are in this zone of this graph. Because there is small amount of water available present in that sand, and this is why it can stick with each other, and you can form that castle. And then a wave of water comes, and despite the force exerted by the wave, even if I ignore it, just because it gets wet, as soon as it gets wet, it loses all its metric suction and all that castle collapse. So this analogy of making a castle, sand castle at the beach, is something which I'm going to try and use to explain the mechanism of landslide as well. This is the exact same phenomenon which occurs in case of landslide occurrence as well, but more to it in the next slides. So this is how the soil water characteristic curves for different kind of soils behave, but I'll quickly move out of it, and I'll move how the rain-induced landslides actually occur. What happens in case of what happens within the soil mass because of which rain-induced landslides occur. So let's suppose we have a soil surface, we have a sloping surface, and in this sloping surface, there is a small soil mass which is there. We consider the soil element. There is a normal force acting on it. This normal force is basically because of the weight of the soil which is on top of it. There is a shear force which is being applied on it. And from the basic soil mechanics that you all know of, we can have a Mohr circle drawn here. And you know, this Mohr circle is far away from this failure envelope for this particular soil. So this is in the safe zone. And as this Mohr circle start touching this failure envelope, we are actually approaching the failure. So in the beginning, we are in the unsaturated zone. The soil is in the unsaturated zone. It is at point A over here. Then what happens? Then rainfall occurs. And as the rainfall occurs, the groundwater table starts increasing. As the groundwater table starts increasing from point A to point B, this, because of the increase in groundwater table, what is happening here is that the soil is becoming more and more saturated. Initially, it was unsaturated, now having a negative pore water pressure, and now it is approaching full saturation, and the negative pore water pressure, which was actually gluing or sticking the particles with each other, it has actually started to disappear. Something that you might remember from the soil water characteristic curve, something that we were discussing. What happens further? There is more rainfall, and as there is more rainfall, because of further rainfall, the pore water pressure starts increasing. See, this soil, which was initially in unsaturated state, it turned into saturated state, and when it is in saturated state, now the pore water pressure is going to turn from being negative to being positive. And when it becomes positive, the effective stresses decreases, and because of the decrease in effective stresses, the slope collapses. So this is the mechanism what happens within the soil mass, because of which the slopes actually fail during rainfall. So there is rainfall. As the rain occurs, because of rainfall, the slope starts absorbing water. As they absorb water, they start losing their shear strength, and they start losing their shear strength, and ultimately the collapse occurs. So this is, in simple words, the mechanism of rain-induced landslides. So this brings me to the end of my second part of my presentation. So again, like before, we can have a quick question and answer session, please. Thank you.
Gee, thank you, Dr. Saab. Now I will continue with the questions where we left in the first session, so that there is no mix-up. The question is now from Miss Aisha Iqbal. For how long we keep on monitoring a landslide-prone area? If past landslides have occurred over there, are there chances that the relevant area already achieved a stable position?
Yeah, I think that's an excellent question. What happens is there are a lot of slopes which, after progressive landslides, they achieve a point where they become stable. But in other cases, there are, and in fact, I'll show a couple of such cases as well. There are other cases where there was landslide, and after some time, there was a second landslide, there was a third landslide. So it all depends, practically speaking, that how much investment we are willing to do for instrumentation or any kind of method on that slope versus the cost of blockade of a highway, for example, or a house that may be affected.
Yeah. Next question is from engineer Suhail Kibriya. He's asking, can prediction methods predict in terms of time too?
Yes, they can definitely predict in terms of time, and in fact, in the next upcoming session, I will show some examples in which I'll mention the time ahead of which we got the warnings and we took remedial measures, etc.
Now we have a question from Mr. Furqan Hamid. He is asking, can we use convergence stations to monitor landslides? And can we use convergence stations to monitor landslides? And further, he is asking, by fixing one convergence point at stable side of the landslide and other on the moving part, and then measuring the distance between them.
I think this is exactly what extensometers do. Extensometers, as I explained earlier, they are installed on one part is installed on the stable part, the other is installed on the moving part. But the problem with all these kind of systems is that they cover a large area on the slope. And I'll show a couple of such examples as well in the next session. They cover a large area on the slope, and because they cover a large area on the slope, their maintenance is very difficult, because your team is going to go to the site, you're going to install the system, and now you want it to be so robust, so small in size, so simple and easy to maintain that you might not have to visit the same remote area for the next 6 months to 1 year at least. So if we have any large-scale instrumentation there, the biggest challenge is its maintenance, even preventing it from wild animals, etc. It becomes a huge challenge actually in these remote areas.
Next, I'm not sure whether it is a comment or a question. It's from Sajjad Saeed, and he has said, value of soil moisture is best for protection of landslide. So maybe he's asking, is value of soil moisture is best for protection of landslide? Maybe this is
I think, yes, we have already discussed this thing in detail, that soil moisture plays an important role. So if this is the question, then yes, soil moisture plays an important role.
Adequately, I think already. Now we have a question again from Mr. Imran, and he's a very active participant in our group, and he's asking, which type of soil has the highest capillarity? What are the reasons for the highest capillarity?
Yeah, I think that's an excellent question, and that gives me an opportunity to come back to the slide that I tried to skip. This slide actually shows the soil water characteristic curves of 3 soils. I'll pick up only 2. There is a clay soil and there is a sandy soil. So the finer the soil, higher is the capillarity. The reason being, smaller the soil, smaller the particle size, smaller would be the size of the void that is inside the soil skeleton. And as we know, smaller diameter capillary tubes, they have a higher capillary action, and the water will rise more in such soils. So this is a reason why fine-grained soils have higher metric suction compared to coarse-grained soils, which have very minimal metric suction. I hope it answers the question.
Yeah. Now, Dr. Saab, we have a detailed question on Facebook from Mr. Yasir Salim. He's in New Zealand at this time, and he's asking a question. It has 2 parts. Is it possible to find the most susceptible location based in the landslide hazard maps, as monitoring of every slope might not be possible? You answer it, then I will read the second part of his question.
Yeah, I think that's very important, and this is exactly what is done. Even instrumenting the whole area is not always possible. So what we do is, it's basically about the cost to benefit things. It's kind of a cost to benefit thing. So we see what is the size of the overall moving mass, and out of this overall moving mass, what is the size which is the most critical one. Like if this part moves, it will cause the maximum damage. So, and what is the cost of instrumenting that that piece of land? So, based upon all these kind of analysis, we come to a conclusion. We come to a conclusion that what size of area should be instrumented.
Okay, now second part, which is connected to the first part, is a bit long. Let me read it. Some slopes are sudden failure where no warning can be given, like debris flow, etc. And some slope failures are long-term where the ground displacement is very slow. How to monitor different slopes like these? Is there a specific technique for each slope? Second question, the sensors used to monitor the displacement are installed at what intervals? For example, a very large slope may need quite a few of them.
Yeah, so can you, Taisa, can you repeat the first part of the question? Sorry, I missed that.
Yeah, it's a long question. I don't blame you. Just let me read it again slowly. Some slopes are sudden failure where no warning can be given, like debris flow, and some slope failures are long-term where the ground displacement is very slow. How to monitor different slopes like these? Is there a specific technique for each slope?
Okay, I got it. So basically, I totally agree with it. Actually, every slope has its own dynamics. When you have to install or when you have to decide that what is the number of sensors to be installed, you have to see at all these things. Yes, there are certain slopes which we know are moving very slowly, and they're moving very slowly for the last 10 years, and they have not collapsed. But we want to understand that in case they collapse, what will be the total potential damage that they may cause. In fact, I'll share a couple of examples in the next session, which will give you some idea of a couple of slopes, in fact, in Pakistan, which if they'll fail, what catastrophe they can cause. So for the long-term slopes, we have to see that. As for the sudden slope failures, again, I would say in the next session, I have given one example where the early warning period, where there was a sudden failure, but still, despite of the sudden failure, there were some indications, and those indications were such that we were able to get a warning of like 2 hours, and those 2 hours are quite significant, at least to evacuate the human beings from there. So had we not relied on the sensors, we probably would have had all the damage without knowing anything. But at least we were able to save people. So this is how the difference is between sudden and long term. And the second question was related to the typical interval. To be honest, there is no fixed interval. The more sensors we'll install, the more information we'll get. It's all like that. I'll try to explain one system there which we were actually trying to develop at University of Tokyo, which was the main objective was such that, okay, in the last 10 years or so, in worldwide speaking, people have developed a lot of early warning systems, but the problem is that they are very expensive, and on a slope you may have to install 10 sensors and the cost becomes enormously high. So what can we do? The other challenge was that the typical systems, you need to have some experts to install them. Installation is a challenging task, whereas the kind of system that we were trying to develop there, that system was low cost and it was very easily installable. The idea was that we need to install it something similar to a fire alarm that you install in your houses, which is run abroad. So this is basically, so there is no fixed interval at which the sensors are installed. It depends on the slope characteristics. You know that by looking at any slope that at least this number of sensors are required. And yes, if you have the budget, you can increase the sensors by, let's say, 1.5x. So this is how this decision making is done.
So Sajjad Saeed is asking, which soil is best protection against the landslide?
Which soil is best protection against the landslide?
Yeah,
I think. Yeah, I think that's a. Firstly, I think let this be the last question for the session, and then we can move on. There is no simple answer to this. Which slope can be best? Anyone having this question in their mind, I would say it depends on a lot of stuff. What you can do is you can take some clay from a pot, and you can take some sand, and you can try to make some slope out of it, and you can see which slope will stand a steeper angle. One. Second thing that you can see is, okay, it was behaving as such, but then you try putting some water on it. And when you put some water on it, you'll see the behavior changes all of a sudden for all kinds of soils. There is no simple answer to this, I think.
Yeah. Very rightly said. That was a good answer. So now we stop the question answer session of this segment here. And we will, when there will be next session, we will start with the questions we already have and they are not answered yet. So don't worry, all your questions are with me. They will be answered by Dr. Saab. So Dr. Saab, please continue.
Thank you, Taisab. So continuing with the last part of this presentation, where I'm going to try and explain some of the case histories of these methods. This is something that we have seen earlier. I've tried to just summarize everything over here on a single slope. If we want to monitor a slope, we need to look at the displacements, and we need to look at the soil moisture. There are different kinds of displacement sensors that are used. There are different kinds of moisture sensors that are used that we have seen earlier. So probably I'll be using terminologies. I'll be explaining how these sensors, one of these sensors, are used in the next one. So I'll be discussing these 5 case histories briefly here. There are one from Seattle, USA, other from Italy, a couple of projects from Japan, and in fact, a couple of years ago we installed some sensors in some near Hunza. So I will not have the data for that to show you because it's a very short time and some other reasons, but I'll at least show you some photographs and some other things related to those landslides. So these two are based upon the traditional landslide monitoring methods. This last 3, I'll try to emphasize the more advanced kind of version of landslide early warning system that we developed at the University of Tokyo. So the first one, this is at the Edmonds Field site in Seattle, and they had a slope over there. And on this slope, if I make a cross section here, so you can see in this cross section. So you can see in this cross section there are. It's around a 45-degree angle slope. So it's quite a steep slope. And on this steep slope, we installed some water content profilers and some tensiometers were installed. I already explained what a tensiometer is. Okay, so what happened was that this initially was the actual ground surface. We had an initial slope failure, and this grade part was which slid down, and it was deposited near the toe of the slope. And after this initial sliding, they installed these sensors over there. This is a photograph which shows the sensors being installed. In fact, this case history is from research that they were doing, and this research actually elapsed more than 10 years. They started it in 2002, 2001, and they published their results in somewhere in 2012. So it's a long research. I'm just showing a little part of that research here. So what they did was they determined the factor of safety of this slope They determined the factor of safety of the slope by numerical modeling, something that we do in Sigma W or other slope stability softwares. By the typical traditional methods, they determined the factor of safety using that. And they also took field observations. And based upon the actual moisture content that you are getting here, those of you who would have done some slope stability analysis, they would know that you need the soil moisture there. And even today, if you are running some slope stability analysis in Sigma W, for instance, it gives you an option to give input parameters for the unsaturated soil. So unless you have the actual data of the soil water characteristic curve, you cannot give the actual soil parameters. So since they had installed those sensors, so they were able to give the actual soil water characteristic curve and actually determine the factor of safety using these. So what happened here? So what happened here was these graphs. I'll first explain what these graphs are. This shows the hourly rainfall. This is the water content. This is the suction stress, the metric suction, that sticky force that we were discussing earlier. So you see, since it is the attractive force, so this is why this attractive force is shown with a negative symbol. It is typical to show this suction stress with a negative sign. So it means minus 16 kilopascals of this suction stress is a higher sticky force, I would say, compared to 4 kilopascals. And then finally, this is the factor of safety that they had evaluated. So what they did was they installed those sensors. They installed those sensors at two depths. They installed those sensors at 1 meter depth and also at 1.5 meters depth. And they saw that when there was rainfall, this is the rainfall event. So because of the rainfall, this moisture content increased at 1 meter depth. This red line here is actually representing the sensors installed at 1 meter depth. So at a shallow depth, the moisture content increased first, and you can see the moisture content increased at, this is when the moisture content increased at the shallow depth, and this is when the moisture content increased at a deeper depth, at 1.5 meter depth. And you can see there is a certain lag in that. A few days had elapsed, probably some more rainfall had elapsed before this water from 1 meter getting seeped down to 1.5 meter. So as soon as the water content increases, you see the metric suction also decreases. So it means with the increase in moisture in the soil, the suction or that attractive force which was binding the particles together, it decreased. It is almost same for 1 meter depth and also almost same for 1.5 meters depth as well. And if you know this suction stress variation by using any slope stability analysis software, you can easily compute the factor of safety. So they computed the factor of safety by using numerical tools, and they found that the factor of safety was hovering somewhere close to 1. It's a little higher than 1. So this factor of safety was hovering somewhere around 1 or 1.2 in this case. So what happened was that there was more rainfall around this time, and when there was more rainfall, this factor of safety at 1.2 meter depth, which was hovering at 1.2, it stayed almost over there. But the factor of safety at 1.5 meter depth, which was already almost close to 1, it means it was all this stage from December 24th, 2005 till January 14, 2016, we were all this time we were approaching the failure. So all this time they were approaching the failure zone, and they had an opportunity to evacuate there. And then finally on January 14th, the failure occurred. So you can see simply by monitoring the moisture, not monitoring displacements, even by monitoring the moisture, they were able to get some early warning for the slope failure. So this was the first example that I wanted to share. The second one is another rock slide in Italy. And in case of this rock slide, we can see that it is again quite a steep gradient. There's a massive rock wedge which comprises of around 185,000 cubic meters of rock wedge, which can be potentially dangerous. So this cross section AA is being shown here at the bottom, and this is the unstable wedge which is shown here. So in this unstable wedge, what they did, they installed a number of sensors. They installed some extensor meters, they installed like accelerometers, thermometers, rain gauges, and besides all these sensors, they did some SAR interferometry as well at the site. Now, with all this background told, these are the results of synthetic aperture radar monitoring that they did somewhere in 2006. So you can see here that by using that SAR results, what they observed was, they observed that this is the uphill side. They observed that the top right-hand part of the slope, the movements were concentrated in the top right-hand part of the slope. So this is where the movements were concentrated. And you can see from this color palette that the red shows a higher movement and this blue indicates slower movements. So they did some radar readings there, and from that synthetic aperture radar, they found that the movements were concentrated in the top right part of the slope. Now, they also installed the sensors. Let's look how the sensors behaved in this case. When talking about sensors, these are all the extensometers that they had installed. You can see all the extensometers which are installed here. This is E15, which is extensometer number 15. Extensometer number 12, 13, 14, and the data transmission mechanism. So these extensometers talk wirelessly. These extensometers talk wirelessly with the satellite receiver, and from there they actually communicated. To their servers. Now, how did it behave in this case? How did the slope behave in this case? Again, let's concentrate on the result of extensometer E11. And what I mean, why I'm focusing on E11, because if you remember from the synthetic aperture radar results, the movements were concentrated in the top right part of the slope. So you see this E11 these are the results of the displacements of E11 extensometer. So this is simply the displacement in millimeter. This shows that this E11 extensometer had the maximum displacement. So maximum displacement was concentrated in this zone as well. And another important thing to be noticed here is that if you look at the trend of the movement of these extensometers, the trend of movement of this extensometer pretty much follows the trend of the rainfall as well. It means as the rainfall was progressing, the slope was moving as well. And historically speaking, based upon my experience, we have seen a number of examples where there was rainfall and there was movement in the slope. The rainfall stopped and it was a dry spell for 3 months, and the slope movement stopped as well. And then there was another rainy spell and the slope started moving again. So this is a common trend that you'll find while trying to predict the rainfalls. So this is another example. Now the question comes here is that, okay, we have seen that this extensometer E11 is showing significant movement, but the big question is, okay, we have seen the movements, but how to decide the failure threshold? How to issue the warning? When to issue the warning to the people? that is actually the big question that is very difficult to answer in most of the cases. Now, what has been done in this particular case is, they divided all the extensometers into two parts. They divided the extensometers in the top part of the slope into one category. These are kind of critical extensometers because we know the movement was concentrated in the top part of the slope. So they divided the extensometers into two categories. One category, the extensometers in the top part of the slope, and the second category with the extensometers in the bottom part of the slope. So they decided to have a different failure threshold for category 1 sensors, which are in the top part of the slope, and category 2 sensors, which are in the bottom part of the slope. And this graph actually shows the results of two of those sensors. For example, this shows results of extensometer E11 and E10. E11 was category 1, having a more critical failure threshold, and extensometer E10 was not that critical. So the failure threshold for more critical extensometers, they set it at 1 millimeters. So they said, okay, when the rate of movement of any of the critical extensometer will exceed 1 millimeters per hour, that is actually our failure threshold. And in case of the less critical sensors, they said, okay, if the value of movement of some of our non-critical or less critical extensometers exceeds 0.5 millimeters per hour, we will issue the warning. So this is the kind of a criteria that they built. But again, it's easier said than done. I am trying to explain it in very simple words. You can see there are so many data points here. How a non-technical person or how even the people sitting in municipality offices can take that decision. It's very difficult for them to analyze so much of data. And remember, this is data only from 2 extensometers. In reality, there were more than 15 extensometers over there. So what they did was they developed this kind of a warning mechanism. What this warning mechanism says, they divided it into an ordinary level operation, attention level, and an alarm level. So what they did in ordinary level, okay, none of the extensometers is exceeding its failure threshold. So if this is the case, routinely check the data and on monthly basis issue a bulletin. But what happens in case of attention level, when the attention level is raised, if 2 or more extensometers exceed their velocity thresholds. For example, if E11 is exceeding its failure threshold over here, and if at the same time this E10 or any other extensometer is exceeding its failure threshold, so we are into attention level then. So if this happens, so in that case, you are to check the data more frequently, and you have to issue a daily monitoring bulletin. So from the monthly bulletin, they shifted to a daily bulletin that has to be issued to locals over there. And then coming to the alarm level. Now, this is important. This alarm level is based upon expert judgment and the use of forecasting methods. What it means is that if you want to raise an alarm, the alarm cannot be raised by people who are sitting in municipality office. Rather, that alarm has to be raised by an expert who understands the mechanism of rainfall-induced failures. This is what they had built. Now, the problem with this is why they did it like this, because raising an alarm is a very, very important matter. In case you issue a false alarm, and there are so many frequent false alarms that there are false alarms and there is no landslide or no damage at all. The people actually start losing their faith in the system. So this is why it is very, very important that the alarm system that you set up, that alarm system has to be very, very reliable. Otherwise, as long as the general population is not going to adopt it and accept it, it's not going to be reliable. So again, you see the problem with this method is that you have to have significant involvement of the experts who might not be readily available at every project site to raise an alarm. So these are a couple of case histories that I wanted to explain before moving to a new technology that is being introduced these days in Japan and now in some other countries of the world as well. And this is a low-cost tilt sensor monitoring based monitoring system. Now, it is low cost, but what is a tilt sensor based monitoring system? What it does? So this is how the basic mechanism of such a system. First of all, if we have a slope like this, on this slope, there are several sensors which are tilt sensors or inclinometers with water sensors. They are installed there. And once these are installed, the data is relayed between these sensors by data is transmitted among these sensors. And once the data is transmitted among these sensors, the data is collected. There is one major gateway unit which is installed. This gateway unit is like the parent unit. It collects data from all the sensors which are installed in that area. So this is kind of a master unit which is installed. It collects data from there and it transfers the data through GSM network, through mobile network. It transfers the data to our server. And once we have the data on our server, we can issue the warning. In a very easy way. So basically, all this data is available today on my mobile phone. So I can simply log into my server and I can see that. And not only this, what I can do is I can have some built-in warnings fixed in the system, and these warnings will be transmitted to me directly. If the sensor exceeds a certain value, it will be exceeded. So the basic component of this is a tilt sensor. This is how a tilt sensor looks like in principle. There is an unstable layer, for example, on the slope. What we do is we simply hammer this tilt sensor into the ground. It is simply hammered in. So this is how easy it is to install into the ground. So you can maybe install one in 30 minutes or so. You install it into the ground in the top unstable part. You see, if I call this as my potential failure surface, what happens is when the slope tries to move, it tries to slide downwards. This tilt sensor, it will get tilted like this. When it will get tilted, so it has the capability to record its tilting in X and Y direction. So it records its tilting and it communicates the data wirelessly to the server for the warning to be issued. So this is how the modern system is shifting towards. Now I'll just quickly share a couple of examples of this kind of a system being effective and being used. One is a Fukuoka National Highway in Japan. And over there, what happened was this red line, this red hashed part was the part which was there, and it dropped, it slid through because of some rainfall. And once this had gone down, they actually tried to flatten the slope a little bit. So you see this shaded part, this is being removed for the remedial work. So they were trying to remove this part for the remedial work. But while they were removing it, they had installed the sensor here. They installed a sensor here. You can get a better idea of this over here. So initially, they had a slope failure in the lower part of the slope, and then they were trying to flatten this part. And while they were trying to flatten this part, since it is a very steep slope, as you can see in this image, it is a very, very steep slope. So what they tried was, they tried to install a few sensors at this critical location that they observed. So they had 3 sensors installed. Out of these, sensor number 2 had a local failure nearby. Now on the next slide, I will show you when this local failure occurred, how the sensor 2 behaved and what happened, what we were able to do. So these graphs actually show the behavior of the sensor there. So you can see this red line shows tilting of the sensor in the lateral direction, like sideways, and this black line shows tilting of the sensor in downward along the slope. So the movement was such that we were not able to get any good data along the slope direction. However, you can see that the sensor started showing some movement, as indicated by this. The sensor started showing some movement a few hours ago, a few hours prior to the actual slope failure. So we were having a nearly zero reading, and when at this point the sensor started giving some reading, or it started showing movement of the slope, it actually raised the alarm bells that there is something wrong which is going on. And because we were able to identify that there is something wrong which was going on, so you can see it is a couple of hours before the failure. So the failure occurred at somewhere around at that 8 hours mark, and probably around 6 hours mark, 2 hours before the failure, we could see the slope moving. So we could not prevent the failure. However, the manpower and equipment over there, it was moved to safety, and we could avoid any loss of human life. So this is one of the case histories of installing such a system. And one important thing is that you can imagine, by looking at this image, you can imagine installing a typical inclinometer or a typical extensometer is not possible at such a difficult terrain. In fact, if we have that kind of tilt sensors, which I had shown earlier, they can be installed quite easily over. Now, another example from Japan, there was a rock cut slope in Japan. It's approximately 20 meters high cut slope. And in this slope, they were cutting from top to bottom. So they had to make a road, they had to cut the slope for the construction of a road. And they were cutting from top to bottom. And by doing so, they installed a single sensor near the top. So this single sensor was installed, and during cutting, while they were cutting it, they saw there was gradual movement that was occurring while they were cutting. So it is obvious that when you are cutting in, you are destabilizing the slope. So when you are destabilizing the slope, there will be some movement that you expect. So what they did there was, this is how the movement looks like. This is when they started cutting, and when the cutting reached a certain level, the movement started initiating. 0.004 degrees per day of movement they observed. But what happened that after this thing, after a couple of days, they observed that this rate has expedited. And you can imagine this thing. This is what typically occurs. When the slope is actually moving, it first moves at a slower pace and gradually picks up pace. So while it was moving at 0.004 degrees per day, the engineers at site decided that this is not a critical range. Yes, we have to be very careful, but it's not causing any danger. But as soon as this rate expedited, they also observed a crack near the top. So they were very careful. They observed the crack. They stopped this excavation activity, and what they did was they started doing some remedial actions. They had constructed an embankment near the toe of the slope to stop this movement, and further they put a counterweight fill over there. And interestingly, once they did these remedial measures, they did all that in 2 days, and 2 days was enough to actually stabilize the slope. And as soon as they put the counterweight there, the slope movement stopped. So this is how this kind of a system, which is a very inexpensive system that you are putting simply just a single sensor, it was able to avoid a catastrophe, which could have been a catastrophe had that slope failed, because there must have been manpower, and there must have been equipment, and obviously it would have stopped work and caused a lot of other issues as well. And then finally, I would like to close this by sharing a couple of examples of these kind of sensors that we installed a couple of years ago at 2 landslide sites near Hunza. So one was called the Homeri Landslide. It's near Hunza in District Nagar. I'll quickly show you how the features are. This is how the slope looks like, and these red lines on the slope, you can see these are the cracks. These are the visible cracks that are available, that are visible there. And right at the toe of the slope, there is Hisper River that flows. This shows a cross section of the slope. So you can see even in the cross section that there are visible surface cracks which are visible on the slope. So I was asked a question regarding progressive landslides. So this is probably what's going to happen in this case. There is going to be this failure at the bottom, and then it is going to progress upwards, and it's going to be a progressive landslides. It is a massive slope which is moving around 4.1 million cubic meters. It's a sliding mass, and it can be very dangerous. These are some actual images from the site. You can see a crack is clearly visible here, and from here in the second picture you can get an idea of the size of the cracks as well. So this is how much the slope has moved over the years. So we installed some sensors at the site. We installed them in October of 2019. After that, we had COVID, and there were some other issues because of which right now I do not have the data to show you. There are some copyright issues as well with our research partners. But anyways, this is something that has been installed there, and maybe at some later stage, I'll be able to share that data as well with you. So, but those slopes we have instrumented. Similarly, this is another slope near Nagar district. It is called the Miachar landslide. Again, it's quite a famous one, and it's quite a significant one as well. The main reason being that this is the huge landslide. Around 1.5 kilometers by 3.5 kilometers is the extent of that landslide. There is a river flowing at the toe, and right next to the river there is Karakoram Highway. So the sliding mass is so significant that if, God forbid, if this slope moves and if it fails, it can be a catastrophe which is much larger scale compared to Atabad landslide. So we had some instruments installed over there as well. This is a picture which can show from where you can get an idea of the size of the crack. And as someone was asking in his question, that, and I explained that sometimes the size of the crack is so big that you cannot install sensors in such a way that you have one sensor on the stable part and the other sensor on the moving part. The size of the sensors, the size of the cracks are so big that it's very difficult to bridge that gap. And you can imagine, even if you bridge that gap, you have to have barrication all along so that it is not affected by wild animals or humans, or it should not disturb the normal activities. So with this, I conclude my presentation. Thank you very much, all of you. And I would be pleased to answer any questions that you have. Thank you.
Thank you, Dr. Saab. Thank you very much. Now we have some questions, and then those questions, after those questions, I will again give you a chance to ask the questions through microphone. So let's first finish the questions which I got in the chat box. Dr. Saab, the first question is from Hasanullah Khan. How the mechanics change in case of frozen soils? Speaking in context of SWCC? Can you answer this question, Doctor?
I think that's a very interesting perspective, but to be honest, I have not thought about it. I have not thought about it with regards to frozen soils. Yes, the dynamics are very different in case of frozen soils because of the expansion and contraction of water in the pores. But that is, I have not had an opportunity to work in such areas which had frozen soil, so probably I'm not the best person to ask this.
Okay, next is from Dr. Suhail Yusuf. He has two questions. The first one is it feasible to have soil mechanics map of susceptible zones in Pakistan?
Soil mechanics map of what, sorry?
Susceptible zones.
With regards to land? With regards to land?
Is it feasible to have soil mechanics maps of susceptible zones in Pakistan? I think he's asking whether we have a map in Pakistan where the sliding is shown. I mean, they are prone to sliding.
Yeah, actually, this is actually the point that I wanted, that I tried to raise in my presentation as well, that all the developed countries, you can easily find such maps from different government organizations, like I had shown for UK. But unfortunately for developing countries and even in Pakistan, we don't have any such things. So I could not find any such thing of credible nature. Yes, you might find some things on the internet, but I could not find anything of credible nature. But I know some people are doing research on this. They are developing maps for localized areas. So for local areas, they might be available.
So his second part of the question is connected to the first, is that what is your opinion on whether such maps will persist for longer times or may change quickly over time?
I think it's a constant race. You have to keep updating them. There has to be there is in fact, in all the developed countries, there is a constant mechanism of updating them and revising them at a regular interval. But I don't think so they'll get outdated worldwide. Reason being, because they still help getting a general idea of building major infrastructure in certain zones. So because of this reason, I don't think so they'll get outdated. Instrumentation is very good for localized areas, but for getting a broader picture of any area, I don't think so instrumentation is of any use.
So now we have two questions from Sajjad Said, and I really don't know how you will answer them anyhow. The first question is, please tell me the name of the city where landslide occur in Pakistan. There would be cities, not city. So would you like to respond, Dr. Saab?
I think a simple Google search would respond better than me.
Okay. Okay. And the second question is, it should have been, I think, vice versa anyhow. Please tell me, earthquake directly depends on landslide?
I don't think so. Earthquakes depend on landslides. Again, it's all the tectonics and other stuff, but I think it's not related, so I should not go into the detail.
This is why actually the question would have been more pertinent. It was other way around. Anyhow, now we have two questions from engineer Suhail Kibria. So he is asking, don't you think that surface settlement markers, in addition to extensor meters, can provide valuable information about the sliding? Surface markers are simple to install and to monitor too. This is his comment.
Yes, I agree, very right. They're very easy to install, easy to monitor. But the problem again is that when we are talking about landslides, they are at very remote places. And again, as I initially mentioned, in case of rain-induced landslides, the numbers are significant. So we install settlement markers, right? But how do we observe them? In order to observe them, we have to go to the site, we have to set up our instruments, and we have to take the readings visually. And again, since landslides mostly occur during rainfalls, so having settlement markers is not going to be any helpful, because during the rainfall, can we take the readings? So that's the problem actually. If we need to have some means of remotely getting the data, I agree that extensometers can be used, as I have also explained tried explaining in my presentation. But extensometers also have certain limitations, which I had tried to explain there. So yes, extensometers, I agree, but unless they are connected with a wireless data system that can give you data at the palm of your hand, I don't think so. This should be the way to go.
Okay, Mr. Kibria's second question is, can you cite any case history where the instrumented prediction indicated an alarming stage and actual sliding took place subsequently when no mitigation measure was taken?
I think the first or the second example of that I had shown, the first example of Seattle City, it had something similar. The factor of safety was constantly dropping, and once the factor of safety dropped below 1, after a few days, the slope actually failed. So this is one example that I think is more relevant with regards to since I've already shown, but there can be many others as well.
Okay, Mr. Hassan Khan is asking how much does it cost the low early warning system that you developed in PKR in Park rupees?
Yeah, I think it's a difficult question to answer right now, but I'll give you some numbers nevertheless. For example, the system that we installed in Hunza, that system did not only had that low-cost system that we were using, because in that particular project, we were actually working with a Chinese university as well. There were some Japanese counterparts as well. The overall objective were twofold. One is to gather data for research and also to prevent those landslides. So because of that, we had to do some extra instrumentation and some extra effort. But what I can say is for a slope of that kind of a scale, you can say probably somewhat close to around 5 to 8 million would be the cost for that large scale slopes over there. But if there is a small slope and if you want to have a quick kind of a system, the cost can be maybe less than half of that.
Next question we have from Kamar Ali Zaidi, and Zaidi Saab is asking, what is the best and most economical method of improving stability of slopes in hilly area of uncertain downpours?
Of uncertain?
Downpours, rain.
So again, it depends from location to location. There are so many variables that are associated with landslides that one method which is there good for one slope not necessarily would work for the second one. But as I responded to one of the earlier questions, that all we need to know the basic mechanics of soil, flattening the slope, adding berms, adding counterweights, adding toe stability, increasing the toe stability, reducing water are some of the measures that can be taken anywhere and they would be applicable.
Yeah, now we have a question again from Dr. Suhail Yusuf. He is asking, what is your opinion about using photo camera and artificial intelligence for monitoring the slopes?
I think that is excellent. That is something that is being done. But I would suggest one thing different than what Dr. Sabha suggested. Instead of photo cameras, it should be on a much broader scale, and it should be from satellite images because that gives you a broader picture. And this is something that has been done globally. In fact, the landslide hazard maps that I've shown, one of the main sources are satellite images, and this is how they do it. In fact, I have a few papers in which people did research in the northern areas of Pakistan simply based upon comparing the satellite images of northern areas of Pakistan over time. They have identified what are the total number of landslides over there. And how they have tried to link them with the rainfalls as well and earthquakes as well. So I think that can be done, but I would suggest photo cameras. Instead of photo cameras, it should be the satellite imaging.
Now we have a question from Furqan Hamid. He's asking, is there any method to predict rock toppling?
One of the examples that I had shown that had rock over there. The problem with rock toppling is that it is very sudden because of the brittle nature of the rocks. However, what gives us benefit is that in most of the cases, we rarely find such failures in an outcrop. there are always, or in most of the cases, there is a thick weathered layer at the top, and beneath that, where there is sound rock, generally failure do not occur. Most of the times, it does not occur in the sound rock. So if we have the top weathered part, in the top weathered part, we can install these kind of sensors. Yes, the moisture readings would not be very good, so I would not suggest that. But the direct movement is something that can be measured there, and it can give us some idea, although not as accurate as it would be in case of some overburden soils.
Yeah, Mr. Zahir is asking, can we monitor the slopes using GIS and ground laser surface markers?
Yes, I think it can be done. And as I said earlier, when people use satellite imagery, remote sensing, and GIS, there are people who are doing that. Similarly, as I shared one example of people using synthetic aperture radars for that. So yes, it can be done, and it is being done. Yes, every method has their own benefits and disadvantages. So it would have some benefits, some disadvantages, but it can be.
Now we have a question from Muhammad Imran. He's asking, are landslides caused by global warming?
If you can link it with excessive rainfall, then yes. If you can, we can link it with this.
Okay, then we have a question from Dr. Suhail Yusuf. No, I'm sorry. He's just thanking you for the highly informative lecture. It is my duty to thank you at the end. Anyhow, please accept the thanks of Dr. Yusuf. Now we have from Mr. Zahir. He is asking, what would be the accuracy? What would be the accuracy of eradicating landslides using these methods?
I believe with these methods, you mean lasers and the GIS methods. I would say the accuracy of these methods depend upon the accuracy of the instruments that you use for that. It depends upon the kind of laser that you're using and how precise is that. Again, how good that laser is to work in a particular environment under different climatic conditions during hot, cold, all kinds of weathers, and during rainfalls, during fog and stuff, how well it can give the readings. So that is something that depends upon the procedure of the instrument that you are using. So there is no definite answer that I have, but I can say it depends upon the sensors and the procedure.
Okay, now we again have a question on Facebook from Yasir Salim, who is located in New Zealand. He's asking, with tilt sensor, is it possible to measure translational and rotational movement of landslides?
Yeah, mainly what we do is we measure the rotational movement, but the mechanism is such that when the slope tries to slide, it slides downwards, and at the same time it is rotating. So it is sliding and also rotating. So we are able to determine we are able to determine both the sliding and also the tilting.
Now we have a question from Hassan Khan. This is how theory and practice should have been combined and delivered. Actually, this is not a question, sir. I'm reading it from the chat box, so I can't read. Questions are coming from Facebook and here, so I don't have a chance to read them in advance. It is just, he's just praising you that this is how the theory and practice should be combined. And he's just praising you, not a question. Hassan Khan, thank you very much for the praise you are making for Dr. It was a wonderful lecture. Now, again, we have a question from engineer Muhammad Imran. Do you think landslides should be part of BSc Civil Engineering course?
I think they already are. The only question is to what extent we can teach them, but otherwise they already are.
Actually, now, if a lot of people are sending the thanks, it is my duty to thank Dr. Saab, the guest speaker, at the end of the session. So let me do my duty, please. So I get confused when the remarks come And whether it's a question. Now, last question from Dr. Suhail Yusuf. It is, what is your opinion on using drones to model surfaces at millimeter level accuracy? How would you use it in landslide monitoring?
Again, I think drones are very effective. They can definitely be used. But again, as of today, the typical flying time of a drone is maybe 30 minutes, max 45 minutes. And that too, we need a clear weather most of the times. Not sure how well they can perform in case of rainfalls and storms. So these are the challenges. If we can have a drone which can keep flying on a certain slope for 10 years, yes, but probably the technology needs to get there. It's not there yet.
Okay, now I am finished with all the questions which were put in the chat box and on Facebook. I have no question in the written form. Now I open the floor for the audience if they want to ask the questions through their microphone. If anyone is interested, please raise your hand. साथी अगर आप भी देखते रहें कोई हाथ खड़ा करे तो प्लीज फेसबुक पे तो खैर नहीं पूछ सकते इधर प्लीज मॉनिटर So, Dr. Saab, I think there is no further questions. Now, on behalf of Pakistan Society of Civil Engineers, I again thank you for delivering such an informative, educative lecture. And it was of a high value, I think, for everyone, young and senior engineers, experienced engineers. That was a wonderful lecture. Your eloquence and your flow of the lecture was excellent. I think everybody understood it with the way you wanted them to understand. This is why we had so many questions. So thank you very much. And I hope we will see you again within this year or next year on some other topic. Thank you very much. And my colleagues here, Rizwan and Suhail, would also be thanking you on behalf of the society. Your certificate and your shield will be sent by courier service by Ms. Sadia, who is our coordinator here, and you will receive it, I think, in a day or so on the address. So thank you very much. And the certificates, CPD certificates for the participants, they can collect it from 16th of June from our office in 32B2 Gulberg Main, Lahore, from 10 to 4 p.m. From 16th onwards. And remember, we are closed on Saturdays and Sundays. Now, the next lecture would be on 10th July 2021. And it would be delivered by Dr. Fawad Ahmed Najam. And the topic is how safe are buildings against earthquakes. And he will also discuss the seismic performance of existing buildings in Pakistan. That is on 10th July. That is on 10th July 2021. So this was an announcement for the next lecture. And now, since everybody lecture has finished, I would again request that you see, don't force me to make announcements again and again. It disturbs the flow of the speaker also. Though Dr. Saab's flow was today excellent, eloquence was there, and but sometimes some speakers do get irritated with unnecessary announcements. So the first rule you have to follow is that keep yourself live on the cam. That is a requirement which PEC has imposed on us for conducting these technical seminars online. So if we don't discipline this online coming on the screen, our license, the permission which we have got it is at risk. So we have to be strict there. And second, keep your microphones in future in mute position so that I don't have to make announcement again. Thank you. And for your information, the society has crossed the 200 mark in the shape of members. Today we have 202 associates of the society. We have already published 10 magazines and 15 newsletters. Dr. Saab, you are such a learned person, learned engineer. Please try to contribute in our civil engineering magazine and newsletter. You can see Rizwan Mirza here on the screen. He's there. He's the editor-in-chief of our publication board. So if you have anything to print, you can always contact him, Rizwan Mirza, or you can contact me, or on our website, the addresses are given. You can contact there. And if you have any research paper to publish, you are free to use our platform anytime. You are most welcome.
Thank you very much, Tahir Saab. Thank you very much, Pakistan Society of Civil Engineers. I had a very, it was very good for me as well to be able to disseminate some of the knowledge that I have. And I thoroughly enjoyed it. And a special thanks to Rizwan Mirza Saab for introducing me to this platform. And in fact, helping me with a lot of stuff as well. So inshallah, I'll stay connected and hopefully we'll be able to contribute as well. Inshallah. Thank you.
Thank you very much. Rizwan, if you are hearing me, so if you can hear me, do you want to say something? Rizwan? Rizwan, would you like to say something?
Yes, it was a wonderful lecture. That's all I can say. It's very good. Very good lecture.
Okay.
Yes.
Okay, so with this, we come to the end of this lecture. And again, thank you very much, all the audience, wherever you are. Now, as you see, PSC is growing. We are having a lot of audienceship on the Facebook and from different parts of the world. Thank you, Zaidi Saab, again, for being here at such an odd time at your location. Thank you very much for being here. And thank you all. Please stay safe. And I'll see you on 10th July. Thank you very much. God bless you.